So in the last video we were looking at measures and methods to determine the efficiency of different algorithms, and we were considering big O notation as a way of expressing the time and space complexity of an algorithm. In this video we're going to compare the different data structures and the operations on those data structures in terms of big O notation. So this video assumes some prior knowledge of data structures and the algorithms associated with those structures. We're thinking about arrays, lists, stacks, queues, linked lists, binary trees, hashing, linear searches, binary tree searches, bubble sorts, insertion sorts, merge sorts and quick sorts. But we're not really looking at the algorithms in detail. We've got videos for each of those structures and the data manipulations on them. So if you're not familiar with them already, you should go back and watch those videos first. In this video, we're just going to touch on those structures and think about them in terms of big O notation. The other thing I want you to bear in mind is that in these examples, we're just looking at sets of numbers, and it really just keeps the illustration easy. It's an abstracted view of a larger set of records. So here we see how those numbers relate to product codes, descriptions and prices, but for the purposes of illustration, we're just going to focus on the numbers. So thinking about a classic array and a list, adding items to the array and list merely means putting them at the end of the array or list, and therefore it doesn't really matter how big the array is. As the array grows, it's just the same operation. So adding items to a serial array and a list is a constant time complexity, so we express this as O1. So imagine a situation where we've scanned a barcode and we need to look up the product description and price. If this data is stored in a normal array in a serial fashion and there's no order to the data, then the only thing we can do is search the items one by one starting from the beginning. So let's assume we're going to search for product code 24. We're going to start at 8, it's not that one. Then have a look at 10, it's not that one. Then 6, it's not that one. And then 24, we found the product that we're looking for. So this is going to be accomplished using a simple while loop. While we haven't found the item we're looking for, search the next item. So as the number of items in our array grows, so do the number of items that we need to check before we find the one that we're looking for, assuming a worst case scenario. Therefore, the linear search is linear time complexity, or ON. Now it's worth quickly stating that if the item we were looking for was always at the beginning of the array, then of course we'd have a time complexity of O1 because it would be constant. We'd always be finding the item because it's the first item that we look for. However, with the big O notation, we have to assume here a worst case scenario, and therefore the item that we're looking for is at the end of the array. So as the array grows, so do the number of checks that we need to perform. Of course, sometimes we don't actually need to search the array one by one. If we know which element that we want to go to immediately, then the time complexity is O1, because the size of the array really doesn't matter. We can pick out any element of the array at any time. So let's have a look at how this compares to a situation where we're maintaining a sequential order to the items in our array. So here we can see that the codes are 4, 6, 8, 9, 10, 16 and 24. They're in order. So now if we want to insert a new item, say product number 7, then all the other items need to shuffle down one in order to make room for 7. So 24 moves down a space, then 16 moves into the space occupied by 24, 10 into the space occupied by 16, 9 into 10, 8 into 9, and then there's an empty space for 7 to be slotted into. So because we're going to be using a while loop or a for loop in this situation to accomplish the insertion, adding items to a sequential array is ON time complexity. As the number of items in the array grows, so does the number of shuffles that we need to perform in order to make the empty space for the new item. However, Having a sorted array gives us a significant advantage because it means we can now make use of a binary search. This halves the set of numbers with each selection, and therefore the time complexity is O log n. So let's assume we're looking for item number 8. Firstly, we're going to find the midpoint and check if it's the item that we found. And if not, we can then discard half of the list and find a new midpoint and check that. Then we can halve the list again and find a new midpoint and check that until we've found the item that we're looking for. So it stands to reason that if we're not adding items very frequently, but we're looking them up extremely frequently, then we're better off having a sequential array, because we can gain advantage of the time complexity of the searching at the expense of the time complexity for the insertion. So how does this compare with stacks and queues? Well, with stacks and queues we've got two operations really, pushing and popping, and because the size of the structure doesn't affect at all the pushing and popping of data, it has a time complexity of O1. It's constant. If we wanted to search through a stack or a queue to see if an item exists in it, then we would have to search one by one, because the items are not stored in any order, and therefore it's got a time complexity of ON. It's linear. So considering how hashing works, we take the item that we're looking for, so in this case 16, we apply a hashing algorithm to it that generates the index of where the item can be found in the array. We then go to index 4 and we've found our item. Therefore, hashing is a constant time complexity, O1, because it doesn't matter how many items that we've got, the hashing algorithm will always generate the index in the same amount of time. However, some codes, when applying the hashing algorithm, would generate a duplicate index known as a synonym, and therefore we have to store that item and look that item up in an overflow table that is simply a serial list in an array. And therefore we are going to have to search that array one by one. So the time complexity becomes linear, or ON, when you have to use the overflow table. This is why we want a hashing algorithm that generates as few synonyms as possible, and we can see that having a constant time complexity is a significant advantage over other uses of an array that we studied earlier. Let's have a look at linked lists. Now these can be implemented using arrays and also object-oriented techniques using objects and pointers. Searching through items in a linked list is exactly the same as searching through items in an array, and therefore the time complexity is linear, or ON. However, the main advantage of this structure is that inserting and deleting items takes no additional processing time. We're not actually going to move any items in the array to maintain the order of the items, and therefore it has a time complexity of O1, or constant time complexity. So when we look at a binary tree, the insertion halves the list every time in order to find the location of the new item, and therefore its time complexity is logarithmic, or O log n. When we search for an item in a binary tree, it could actually be linear and ON complexity. But in an ideal world, you'll find that you're halving the list every single time, and therefore the time complexity for searching a binary tree will also be logarithmic and O log n. So here we're looking for item number 24 again, and we're going to start at the root of 8, and then we're going to work out that 24 is greater than 8. So we're going to follow the right hand branch and we're going to discard everything on the left. We're then going to compare 24 to 10. 24 is greater than 10, so we follow the right branch and we can discard everything to the left of 10. And then we find the item that we're looking for. So whilst a binary tree is not the best in all situations, it certainly is a great compromise because of its logarithmic complexity over the other data structures. The bubble sort and insertion sort use nested loops, and therefore their time complexity is ON squared, or quadratic complexity. The quicksort and merge sort are a little bit more complex. In worst case, the quicksort would be on squared time complexity, and the merge sort is a little bit beyond the specification in terms of calculating its time complexity. Now, one thing that we haven't really considered much is the space complexity, or the amount of memory that's going to be required for each of these data structures and algorithms. But to be fair, they're all really linear. So as the data grows, then the memory requirements grow. So the space complexity is ON. There are also a few quick tips that would be helpful for exams, for you to spot in an algorithm what kind of complexity it's using. So if you've got no loops at all, then it's probably constant, or O1. If you've got a single for or while loop, then it's likely to be linear, so ON. If you've got a loop inside a loop, which we called nested loops, then it's polynomial, or ON to the power of the number of loops. If you're halving a data set, then it's logarithmic, or O log n. And if you've got a recursive function, look to see if it calls itself twice, such as a Fibonacci sequence, in which case it's going to be exponential, or O2n. So as a final thought, there are two ways of calculating a Fibonacci number. You can do it using a simple iteration, in which case you're going to have linear complexity, or ON. You could also do it using recursion, in which case you've got exponential time complexity, or O2n. So we can see, just using big O notation, that an iteration is going to be better than recursion. It's also true in terms of the space complexity as well. This is how we know that recursion, although it's easy to program, is actually not really a good idea.